Don't need this one. Where did we leave off? Let's see. One sec. Okay. I think this is us. Last time we talked about... Okay, we were naming stuff. Oh, sorry, we did the crazy naming. Okay, cyclic stuff. Okay. Then, let's go ahead and get started. So, cyclic alkanes. We see that if we have cyclic structures... That's really a terrible drawing of a pentagon. I'll try and make it a little better. There we go, that's a little better. When we talk about cycloalkanes, those are, behave much like alkanes do. We see that when we're naming things with cycloalkanes, we just include the cyclo prefix with them. So this would be propane. This one would be cyclopentane, cyclohexane, and the one I've omitted, cyclobutane. So, very exciting here. So instead of having a chain of carbons, we have a ring of carbons. So these are all connected together in a ring structure, and we would call those cyclo whatevers. We would name them much the same as we would. Generally, we will have the ring as your parent name. Usually it's easier to do so. However, sometimes you'll see it's easier to make your parent not a ring. Like with that example with Kevin had posted in Discord about the 2,3-cyclohexyl dicyclohexyl butane. It's a little bit easier to name it that way than to try and name the ring as the parent structure. So generally, though, if you have just a bunch of substituents on a ring, oops, not going to do stereochemistry on this yet. You would just name them and name cyclohex or cyclic alkane as your parent. So we might say for this one, we have 2 chloro, 1 isopropyl, 3 methyl cyclohexane. There should not be a space there, but because I always run out of room, we had one. So it's much the same as before with this. You just have a cyclic thing as your name. You can name them as substituents if you like, and sometimes it makes more sense to do so. Like with this one, you can say this is 3-cyclopropyl 1, 2, 3, 4, 5, 6, 7 heptane. So they can be substituents, they can be parents. Generally, it's about whichever one's longer. If your ring is, more substituted, or if it's got more carbons, generally you might name the ring as your parent, though you can name them as substituents. It's really just kind of whichever's easiest. Like, you would never name this first compound like, base it off of this propane or something. Like, you wouldn't do that, right? It makes no sense to do it that way. So it makes more sense, though, to name this one with the cyclopropyl as a substituent, because otherwise you're going to have to then throw in all these other things. We would have to say it'll be 1 parentheses 1 ethyl 1, 2, 3, 4, 5 pentane, pentyl cyclopropane, which is a pain. Nobody wants that. So easier to sometimes name your ring as the parent, sometimes easier to name your chain as your parent, but really the same thing when it comes to cyclic alkanes. All right, let's see. Do we have any special alkanes? I did ask this in the homework because it was at one point important, but this molecule here, it is no longer called this, I apologize, but in the homework I asked you this. It was changed in, I think, I don't know, like 5 years ago, and I just haven't updated anything, but this guy here is neopentane. This name is no longer used. Now we would just call this 2,2-dimethylpropane. Or if we were really smartasses about it, we could just say dimethylpropane, because there's no other places those methyls could be except carbons 2 and 2. Either of these are fine. So I do ask you neopentane structure. Don't worry about that naming convention anymore. It is no longer used. But it's the simplest quaternary carbon we have. So a carbon with 4 carbons on it. So fun stuff. The reason that we used to think, like neopentane is so cool, if you think about all the isomers of pentane, you have the linear structure. You have the one branching, and then you've got the kind of neopentane structure. And if you were to burn these and get delta H's, all of these have the same molecular formula. They would all burn the same way, make the same numbers of carbon dioxides and oxygens. I'm sorry, carbon dioxides and waters. We would see that delta H1, the magnitude of it, absolute value, is the greatest of them all. Which means there's the most energy associated with it. We do see that in general, kind of the more branched alkanes are more stable. It's a minor trend, but it's something we can talk about with alkanes. These are minor amounts of energy, but still, this is why we would talk about these things. We would say pentane, isopentane, and neopentane. We would talk about their delta H's, and we would see that the neopentane has the lowest delta H, magnitude-wise, when we're comparing it after burning things. It's really not so relevant anymore, but suffice it to say that more branched your alkanes happen to be, the more stable they are. It's just a fact, for combustion purposes at least. So there's some energy gains to make more branched alkanes than there are to make linear alkanes. So, but that's all well and good, but we don't need to really worry about that anymore. So, let's talk about ways to display alkanes. We're going to have kind of 3 major ways that aren't the way we normally look at molecules in a wedge dash format, or in this case just zigzag. We don't really have any substituents because these are all hydrogens. If you really wanted, though, remember that we have hydrogens on wedges and dashes here that are just normal. We have our wedge dash, which is kind of our go-to ways of talking about alkanes. But if we really want to kind of look at some of the things that alkanes have to deal with in their everyday lives, we have other kinds of what we call projections. We're going to see we have what are called Sawhorse projections. We have Newman projections and Fischer projections. I think there's a... Is there a C in Fischer? I don't remember. There may be, there may not. I don't remember. But these three are kind of ways we can talk about alkanes. And when we're looking at them, if we're, say, looking at butane, the Sawhorse and the Newman projections will look at things along one bond. And so if we're looking at things along a chemical bond, a Sawhorse projection will kind of show us in 3D kind of what things look like along that bond. We might say, if this is our, we might even say methyl. We'll just be a little bit neater about it. We might say, for butane, which is a 4-carbon structure, it is with a C. Okay, cool. We can never remember. Half the time it's with the C, half the time it's without. A Sawhorse projection looks like this. It's kind of, I don't know where the word sawhorse comes from. I think it's a gymnastics thing, from what I may or may not remember. You essentially are looking along a bond, whichever bond you're looking at. We'll talk about how to convert between these later on. You're looking along a bond, and you're looking at it kind of from the side. So you'll have one carbon, you'll have the bond between it and the next carbon, and you're looking at them from the side. A little bit of an angle. So we can see kind of those two carbons that we're looking at, here and here. Those are the carbons of the bond we're focusing on, and we're looking at them from the side. So we can kind of look at what substituents are on those carbons, and we'll be able to focus on those if we want to. With a Newman projection, it's the same idea, except we're going to be looking at a molecule head on. So if we're looking at that same bond, the way a Newman projection works is you're going to focus on kind of your first carbon in the middle and your second carbon in the back. So I'm going to draw the same thing. A Newman projection looks like this. So it's the same molecule. In Sawhorse, we're kind of looking at things. We like to draw our eyeballs, by the way. So in this butane molecule, here's our eye. We're looking at this bond right here. And we see, aha, well, that's a CH3. That's a methyl group. That's also a CH3. So if we're looking at those two carbons that I've put as dots, at what they have on them, we might get one of these two projections. If we're looking at the side, we get a Sawhorse projection. So if we're looking at that bond, we see pointing down in front of us is a methyl group. And then we also see in the back, we have a methyl group pointing up on the second carbon, on the back carbon. And so both of these projections are showing us the same thing. One from the side, that's Sawhorse. One straight on, that's Newman. And so we're going to see that these projections are going to be very useful for talking about how things rotate in energy barriers, as well as determining kind of stable states of things. And so this is kind of how I'm getting these two. So I'm looking at that carbons 2 and 3 of this particular one. This is carbon 2. That's carbon 3. This dot in the middle is carbon 2. This round thing is carbon 3. And we're just looking at what's attached to all those. On carbon 2, I have a methyl group that's pointing down. If I'm looking at the molecule from that angle, from above, like that, we see a methyl group is pointing down. And if we look on carbon 3, in both cases we have a methyl group pointing up. So these molecules, again, or these projections, ways of viewing molecules, show us the same thing, but in a slightly different way. A Fischer projection, though, on the other hand, is a little bit more complicated. It's more useful for sugars than anything else. But the way that a Fischer projection works, and it's maybe not so obvious with this molecule because everything is just carbon and hydrogen, every kind of vertical line is a dash in a Fischer projection, and every horizontal line is a wedge. So that would be like saying, if we're looking at this, we're looking at it from above now for a Fischer projection. We're putting it so every time you're looking at a kind of vertical line, that's the up and down part there, those are all dashes, so they're pointing down away from us. And everything that is on a horizontal line there is a wedge. And so it's terrible, but we might be like kind of looking at something like this, where we just have, oh, that's not important, but so every kind of carbon we look at in a Fischer projection, it's kind of terrible to do without a model, but suffice it to say we're looking at everything from kind of above. So we have the hydrogen sticking out at us, and all the other carbon-carbon bonds are pointing away from us into the paper. It's, again, more useful for sugars than it is for structures like these, but it's still going to be useful for us to be able to convert in between them. Hi, Oz, you want to come say hi? No, he just waddled in and is standing in the doorway. So Fischer projections a little bit harder to see right now. We'll talk about making them a little bit later, but I just do want to kind of start with putting them all out there so we'll see the various things we're going to look at when we look at projections of molecules. Alright, so again, with a Fischer projection, everything that's vertical is, pretend it's a dash. So if you're looking at this carbon, if we're just looking at that carbon there, if we look at what's attached to that carbon, we have a methyl group, we have an ethyl group, and we have two hydrogens on wedges. So that's what that's showing you. Each kind of, that's that blue carbon that I've indicated on the Fischer projection there. Let me go back up. So that carbon there has an ethyl group. Hopefully we can see that's an ethyl group below it. Two carbons is an ethyl group. We have a methyl group above it, so those two are both going to be on dashes. And then the hydrogens are on wedges, because those are horizontal lines. So, very fun, I know. We'll talk about these projections more. We're going to focus first on the Newman one, because that's going to be the easiest for us to see how things are interacting as we go along. Okay, so let's talk about Newman. Let's talk about first our favorite molecule, ethane. If we were to draw this as a skeletal structure, there it is. A line. If we want to put this in a Newman projection, remember, in Newman projection, we're looking at a carbon-carbon bond. In this case, there's only one. We see, again, this dot here is your front carbon, wherever you're looking at the molecule. This is your back carbon, a large circle, and then we're going to have things sticking out of it. I'm going to sneeze here. Excuse me. So that's how a Newman projection, kind of the basics, look. If we look at these carbons, the front carbon has 3 hydrogens on them. We always draw everything with their angles. So they look like 120-degree angles here because we're looking at them dead on. In reality, they're 109.5 because these are tetrahedral, but we can pretend. With the back carbon, I'm going to draw these. Actually, let's draw them in different colors. So the back carbon is green. And all these stuff on the back carbon has these kind of shorter lines to it. It has the short lines that connect to the big circle. The stuff on the front carbon oh no, that's our front carbon. The stuff on our front carbon, I'm gonna have so many freaking arrows here, I apologize. Those major lines, I have an idea. Let's reverse all this stuff. Okay, I can work with this. Okay. I'm gonna redraw it. So that's the stuff on the back carbon. They're the shorter lines that connect directly to the big circle. With the front carbon, the stuff on the front carbon are these things with the longer lines, the ones that connect to the middle dot. Those are the things on your front carbon. So in ethane like this, since everything is hydrogen, we might draw it like this. And again, we're going to focus on Newman projections right now, but we will talk about Sawhorse and Fischer projections, if not this chapter, then next chapter. So, but right now, Newman is kind of our go-to. And we're going to see, because carbon-carbon single bonds, like any single bonds, they have free rotation. These things can rotate around. And so the Newman projection is particularly useful for evaluating things as they're rotating around. And so we're going to see if we rotate one of these carbons, we're going to end up with something a little different. And we're going to see the energetics of it. So starting off, here's our happy Newman projection of ethane. Again, those 2 dots, the dot in the middle is the front carbon, the big circle is the back carbon. And then we just put on everything that's on it. All of them have hydrogen, so it's not very exciting. But suffice it to say, if we were to rotate which one shall we rotate? The front one or the back one? Let's rotate the back one. 60 degrees, not Celsius. 60 degrees. Let's rotate it counterclockwise. And I'm just gonna go ahead and label these just so we can see them as they are rotating. If we rotate this, I'm gonna move this up just a little bit so I have a bit more room. So if I'm rotating this guy counterclockwise, that would be that way, right? Our front carbon stays the same. And now we've got all of our bits here kind of scrunched up right next to each other. This is H1, that's H2, that's H3. I've just rotated them all a little bit counterclockwise. So I've rotated my back carbon 60 degrees counterclockwise. As a result, we now have them kind of sandwiched between each other. And we're going to see that if we were to just kind of look at energetics here, this, if we say this is like kind of state 1 and state 2 of it, we're going to see that state 1 is of lower energy than state 2. And I have numbers here. 12 kilojoules apparently is our number. You don't need to know this. But this rotational energy is about 12 kilojoules per mole. And let's investigate why this is higher energy. So as this molecule rotates, totally again free to do that because it's a single bond. Single bonds rotate all the time. We're going to see as, say, that back carbon is rotating around, spinning around, it occasionally, every 60 degrees, is going to kind of go between two states. We're going to see it's actually going to keep going like this. As we keep rotating 60 degrees. Counterclockwise. If we just keep rotating, if we rotate it again 60 degrees counterclockwise, we end up with the same thing that we started with. And I'm gonna just copy it here. If we rotate it, and then we'll talk about why state 2 is higher energy. And I'm gonna change the numbers now because they're different. If I rotate this again, now hydrogen 1's there, hydrogen 3's there, hydrogen 2's here. The ones on our back carbon. So I just keep rotating 60 degrees counterclockwise. I basically go between the two states, right? State 1 and 3 are the same as each other. And we're going to see if we have a state 5, it would also be the same. States 4 and 2, 4, and 6 would be the same as each other. If we want to look at these, we say, oh, well, we can talk about these. Number 2 is going to be higher energy. Let's see if I can fit all of this in here. Because those orbitals are going to kind of be bonking into each other. The orbitals that contain the hydrogens. So as this molecule is rotating around, which again it does constantly, 12 kilojoules per mole is not very much, but it's rotating around, and every so often, every 60 degrees, those hydrogens are going to kind of come in contact with each other. We don't typically draw the kind of out-of-phase side of the sp3 orbitals. We usually just kind of draw them like this, right? That's how we normally draw the sp3 orbital. That's an sp3 bonding orbital. The sp3 anti-bonding orbital is the opposite. It's kind of the opposite side here. Suffice it to say, though, when things are rotating and they are kind of occluding each other like this, when they're hitting each other, we end up overlapping the anti-bonding side of one orbital with the bonding side of another, and that's not a good thing. So we have some minor overlap there, kind of electron density repelling each other. It's as if we had, just the balloons, and as we're rotating the balloons around, they kind of get a little scrunched, and so they're not so happy. And that's the higher energy state. It's the same thing. We're just kind of rotating things around. We have some occasionally bad overlap. And so, without focusing too much on the orbitals, suffice it to say it's a bad thing. Not a terrible thing, but a bad thing to have these overlap with each other. And we have names for these. We call this one an eclipsed. Is that how we spell eclipse? Yes, it is. This one we will call eclipsed because the hydrogens are kind of blocking each other, right? The hydrogens from the front ones are now kind of bonking into the hydrogens on the back carbon, and they're eclipsing each other as if it were a solar eclipse or something where the moon blocks the sun. Or is that a lunar eclipse? I'm not an astronomer. One of those two. The eclipse idea here is one of them, they're blocking each other. So when they're overlapping like that, we call that eclipsed. When they are completely away from each other, we call that staggered. So if any of you are in a chorus, you will stagger your breathing on sustained notes so that overall things are, everybody's breathing at a different time, so that way overall it sounds like there's no change. It's called staggered breathing. It's the same idea here, where everything is nicely separated from each other, and that's called staggered. So 1, 3, and 5, I've not drawn 5, but it's the same as 1 and 3. Those are staggered conformations. 2, 4, and 6 for this molecule will be eclipsed conformations. So these are called conformations. 1, 3, and 5 are all staggered. Those are the lower energy conformations. 2, 4, and 6 are eclipsed. Hopefully, so far so good. We're just kind of rotating things around 60 degrees every time, and we end up having some fun, good stuff here. If we are to look, the book makes a big deal of this. I don't think it's a big deal, but if we take into consideration that this is about a 12 kilojoule per mole process to rotate between them, again, not a huge amount of energy. But if we see that there's kind of 3 hydrogens bonking into each other, right? We have this pair, and this pair bonking into each other. That suggests that each kind of bonking pair of hydrogens is about 4 kilojoules of energy there to make those two eclipse each other. We'll see later on when we start replacing things that are not hydrogen with other things, we'll see that we'll end up with different energy gaps. Again, I'm not going to make you memorize these or anything. Excuse me. I just want you to just kind of have an idea of the energy differences. So are we so far so good on this idea of how things are rotating and using these Newman projections? We're going to have plenty more, don't worry. All right, let's go ahead and start looking at propane then. So this was ethane. Everything is hydrogen. If we look at propane, it's not going to be much different. And so if we are going to put propane, let's say here it is, propane. If we take our handy dandy eyeball, there we are, we're looking here at these two. So this will be our front carbon. This will be our back carbon. If we look at our front carbon, we have got a CH3 pointing down right now. And we have 2 hydrogens. And our back carbon, we've got 3 hydrogens, because it's just a methyl group in the back. We'll see propane is really not so much different than the others. We're going to see if we rotate propane. Same thing, let's do the, let's rotate our back carbon 60 degrees, counterclockwise. Front carbon stays the same. Again, you could rotate either one. I've chosen to rotate the back carbon because I felt like it. I would either tell you rotate the front carbon or the back carbon X degrees, and you should be able to do that. If we rotate the back carbon 60 degrees, we now have our eclipsed conformation. So remember, this is still staggered. This one is eclipsed. And if we keep rotating, we're just going to go back and forth between the staggered and the eclipsed, right? There's really no difference between one staggered and the other staggered. And so we're going to see here, we're going to have the same kind of energy diagram as we go through. So from state 1, 2, 3, 4, 5, 6. This will be what states 1, 2, and 3, 1, 3, and 5 look like. 2, 4, and 6. It's really much the same. The energy gap here, 14 kilojoules. If we suggest that the HH difference was about 4 kilojoules, if we just plug that in, we see that if we go ahead and see how this is going to add up to 14, we're going to see that a bonking between a methyl group and a hydrogen is about 6 kilojoules. So, minor difference. We'll see once we throw in butane, things are going to get a little bit more exciting here. So propane, much the same story. We just have a slightly bigger energy gap here, but still we're going to have two basic sets. We have 3 staggered conformations and 3 eclipsed conformations as this thing is rotating around. So 1, 3, and 5 will all be the same as each other. 2, 4, and 6 will all be the same as each other as things are rotating. Let's look at butane. Butane will be more fun. Let's do the same thing. Eyeball. Looking at front carbon, back carbon. Our front carbon, we have a methyl group pointing down. We have hydrogens sticking out. And in the last case, in our back carbon, we now have a methyl group pointing up. So, now we can rotate things around. I hope I have enough space for this. I probably don't, but that's okay. So, let's rotate our back carbon 60 degrees. Let's rotate things. Our front carbon stays the same. Our back carbon now. Oops. I put that on the wrong side. Shame on me. There we go. Alright, so we have our back carbon now rotated. Not so great. Let's rotate it again. Let's keep rotating it. Let's see what happens in the next state. So that's a type of eclipsing, right? Not so great. In this case, though, we have a giant back carbon. No. If we're looking at our next state, this one is not the same as the first state. Right? Here is 1. Here's 3. 2, whatever is in the middle. Do we see a problem with how is 1 and 3 different? How are those two different? Well, hydrogens are relatively small, right? They're just single atoms. We now have, though, two methyls that are kind of close to each other. We should see, hopefully, that for 1 and 3, they're different because in the first one we had the methyls as far apart from each other as possible. They were the opposite sides of each other. And then as we got kind of more and more, as we keep rotating, we see now we have the methyl in the back that's kind of close to the methyl in the front. And we're going to see there's more likelihood because they're bigger, a methyl group is much bigger than a hydrogen is. There's much more chance that those are going to bonk into each other as things are happening. So we can have some kind of like clashing here a little bit. A little bit of clashing that we wouldn't normally have between, say, here and here. Like those don't really clash, right? Because the hydrogens are so small. But now we have a methyl group that's got 3D stuff on it, more likely to clash. And if we keep rotating, same direction. Let's take a look at this one. Oh ho ho. This is even worse. And hopefully we see why it's worse. Because now those methyls are definitely bumping into each other. We saw even just having the hydrogens bump into each other was problematic, 4 kilojoules per mole. A methyl and a hydrogen, 6 kilojoules per mole. Let's see what we have here. We're looking in this case at about 11 kilojoules per mole, so twice as bad now. We'll see this in a sec, though. We'll talk about it. And if we keep rotating, we see number 5 will be essentially, it's a mirror image of number 3, but I'll keep drawing them. If we keep rotating, number 5 and number 3 here are really essentially the same, right? We just have the methyl groups kind of near each other, and they're going to be kind of not so great, but still better than 4. And then as we go to 6, we're going to see it's much the same as 2 was. So we have now kind of our CH3 bonking into the hydrogen. We have the hydrogens next to each other, and we have the hydrogens next to each other. Our hydrogen now bonking with the methyl there. So this is much the same as number 2 was. So you see here we had HH, H-methyl, H-methyl. Those are the interactions we had. So much the same as number 2. Number 3, we had just kind of those side interactions. And on number 4, we had HH, HH, and methyl-methyl. So that's a different thing. If we were to kind of graph these, we're going to see our happiest state is number 1, right? Where everything is kind of far from each other, and that's our best conformation. That's going to be our lowest one, number 1. And we saw that number 4 was kind of the worst, where we have those methyls directly next to each other. And so as we kind of go through this, our graph, oops, I need to have that on number 5, whatever. And then it goes to like there, and then back down to whatever. Ooh, I'm so good at drawing. So we see that state 1 was our lowest energy. We had our bulkiest groups as far from each other as possible. In number 2, we had a staggered conformation, which is going to be relatively high energy. And then we kind of went, I'm sorry, that's an eclipse. That's eclipse. Number 2 is eclipsed. In number 3, we went back to staggered, but it's not as good of a staggered as number 1 was. We have a special name for this. We call this one gauche. And I don't know how to spell. This is a gauche interaction. In French, gauche means left, as in left hand, right hand. I don't really understand the relationship of gauche to molecules like this, but that's where the word comes from. So these are interactions that are kind of not as bad as eclipsed ones are, but they're not as good as fully, like, happily staggered ones. And so these are kind of what 3 and 5 would be. 5 would also be gauche. And that would correspond with these kind of, they're higher energy than number 1 was. So they're still kind of staggered, but they're not quite that good. These would be our gauche ones. We're going to see that 2 and 6 are going to be eclipsed. Just like before, 2 and 6 have eclipsing happening. But number 4 had the worst one. So if we were to try and predict the energy of number 2, we would say, well, we know a HH is 4, and a methyl H is 6. So 6 plus 4 is 16. So we'll say that that difference there is 16 kilojoules. Again, I don't need you to memorize these numbers. We're going to see that number 4 is 19 kilojoules. So we're going to see that a methyl bonk is about 11 kilojoules. Right? We have 2 HHs. Each HH is 4. So 19 minus 8 is 11. That gives us the 11 kilojoules for the methyl interaction. So again, higher energy. This is also technically eclipsed, but we have a word for it to describe it, and we call this one syn eclipsed. So syn eclipsed means you have the worst case scenario. Oh my gosh, stop trying to convert all my things to... There we go. So where we have our biggest groups on our molecule interacting with each other, that's the syn eclipse, when they're directly eclipsing each other. So syn eclipse right here. So we have words for those kind of eclipsing where it's not as bad. We just call those regular eclipse. We have the extra bad eclipse, which is syn eclipsed. We have these kind of staggered ones that we had before. I'm totally out of color. Oh no, wait, we have purple. Okay. Fully staggered, which you might even call anti-staggered, where things are the opposite side of each other. Our biggest groups are as far from each other as possible. That's our lowest energy state. Our second lowest energy state is where we have those big groups kind of near each other, which is called gauche. And kind of our high energy states, we have the eclipsing of our not as big groups. And then finally we have the Eclipsed, which is the worst one of them all. So those states here, I know are here. I can, for right now, let's flip it over. Let's do this way, so we can at least see all of them. So molecule 1, our bulkiest groups, the methyls, are as far from each other as possible. So that is our lowest energy state. We call that anti-staggered, or just staggered is fine. If we rotate 60 degrees, we end up now eclipsing some of our substituents. We have 2 methyls eclipsing a hydrogen, and we have 1 hydrogen eclipsing another hydrogen. We keep rotating. We now have our methyls nearby each other, even though it's staggered. We call that gauche. It's higher energy than number 1, but not as high as eclipsed. Keep rotating. We now have our biggest groups right next to each other. That is syn-eclipsed, highest energy. We keep rotating. We go back to gauche and back to eclipsed, and then finally we'll go back to anti-staggered with our, if we go like to number 7, which would be back to number 1. So, I mean, it's so fun to talk about how molecules are rotating. So, but this is stuff for homework. I will have you kind of work on your own about evaluating what's called conformational analysis. Do I have that on our current homework that's out? Where did I put that? Let's see. I'm pretty sure I have this. We've got Newman Projections there, chair conformations, line angle, IUPAC names. Aha! So question 8 in this, we'll talk about this sort of conformational analysis. So for number 8 for your homework, you're going to be doing something just like this, but you're going to be using a different molecule. So this is just butane. Number 8 on the homework is 2-methylbutane. So you're going to have an extra methyl group on there. So part of your homework, you're going to be developing a graph like this, as well as all of these kind of things. So for number 8 on your homework, you do this for this molecule. And again, you're looking at this this bond here. So you're looking at carbon 2 and carbon 3. You're looking at that axis. And so you're going to be doing essentially the same thing, but you're going to see the you're not going to get exactly the same graph as this. Ideally, if you like, go ahead and figure out the energy differences. You can do that on your homework because you'll have these in front of you. But I'm not going to ask you on an exam for the energy differences. So just remember, staggering or eclipsing 2 hydrogens is about 4 kilojoules per mole. Eclipsing a hydrogen and a methyl group is about 6. Eclipsing 2 methyls is about 11. So I do want you to label all the energies between your lowest conformation state, which is fully staggered, and your highest, as well as these kind of eclipsed or gauche, or the gauche ones you don't have to worry about, but the eclipsed ones. So that's what I want here. So you'll see what this is going to look like. But go ahead and do that. So you're going to do the same 6 sort of things. So you'll have 6 different angles. Those are 60-degree rotations. You can rotate either the back or the front carbon. Take your pick. You can rotate them clockwise or counterclockwise. Take your pick. I chose back carbon counterclockwise. You could choose front carbon counterclockwise. Or front carbon clockwise, whatever. It's all good to me. However, one thing I do want to pay attention to is notice on all my eclipsed ones that I have consistency where my back carbon is in relation to my front carbon. What I mean by that is notice that on this one, my front carbon is slightly to the left of my back carbon. If I'm looking at that H, like straight on, if I'm looking this way, or sorry, I guess this way for our mirror image. I don't know. Am I mirror imaged on Twitch? I don't know. Am I going left right now? Or right? Let's see. I'm going to keep going. Okay, so I am mirror imaged. Okay. So if I'm looking this direction, right onto that carbon and methyl, my methyl is slightly to the right of my hydrogen. All right, so that's what I'm looking at there. If I now look on my left side, if I'm looking at that front hydrogen, we're going to see again, my back carbon is slightly to the right. If I'm looking down at my methyl group, my hydrogen is slightly to the right. So just be consistent there. So you don't want to ever have two things on the same side. So what I mean by that, oh no. This is a no-no. So you can see on that one, I've now made it some sort of like 90-degree angle or some weird stuff. So you want to make sure that you only have like one thing in the gap from your front carbon substituents. So keep just be consistent. So if you put something just slightly before your front carbon, then leave it all the same way. Okay, so keep everything nice and consistent there on your Newman projections. Alrighty. Oof. So those are our kind of like Newman projections. So number 8 on your homework, you'll be doing this sort of thing. All right. Any questions on that? Oh, by the way. BTW. I've been asked to do a review, kind of like more open, quick office hour type thing, which I'll just call a review session. We can do that on Friday, where you guys just come and ask questions and I'll do it. We can do it in Discord, so we don't have to like put it on Twitch. And if you can you can ask them directly if you want. We'll do that. I'll still record it though, but not on Twitch. We'll have a review there on Discord. Either 9 to 10 or 10 to 11. I'll put a little poll up for which time you'd prefer, and we'll do that. And so that'll be up later after class if I remember to do that. And so we can have a review and you guys can ask questions and stuff. You can do it verbally or written. Either way is fine. So yeah, we'll do that on Friday. This Friday between one of those two times. Okay? So whatever questions, doesn't matter. We'll go over whatever. Cool. So I'll put that in Discord. Someone remind me if I don't. It'll be very much like polls we've done in previous classes where you just will choose the emote that you like. If you like both, go ahead to vote for both. Whatever. Yeah. Cool. Okay. So that'll be Friday. But back to this stuff. Let's talk about cycloalkanes again. So, some cycloalkanes. I feel like I just did this. That's 7, right? What's the bond angle for a heptagon? 135. Okay. If you are a carbon of the tetrahedral variety, which we all are, right? Which of these two would probably be your most like ideal ones? Carbon should have a bond angle of 109.5, right? That's our tetrahedral bond angle, which is somewhere in between these two. And indeed, we do see that these are the most two stable ring structures. We see that these guys have a lot of what is called ring strain. Before, with these Newman projections, we might call this sin-eclipsed idea torsional strain, where it's about turning things. We might call this a torsionally strained conformation. What color shall we use for this? How do I spell torsion? There we go. So we have strain here. As we're rotating this, we find something that's not so great. That's a high energy state that is straining it, straining the molecule, making it a little bit less stable. We have the same idea happening in rings when we call this ring strain. We can have torsional strain in rings too, but we'll see that ring strain arises from the fact that these angles are really not what carbon wants to be. They're forcing electron domains closer together, which is not a good thing. And in reality, these aren't the angles that we're looking at. These are angles from geometry class. But in reality, the angle in a cyclopentane is about 72 degrees or so. Because you actually end up ballooning outwards a little bit, so it's not a perfect triangle. You kind of make a triangular circle. It looks more like this, rather than an actual triangle. So in reality. So in really, you end up with about 72 degrees, but still that's not great. You want 109.5. So we'll get rid of that. You don't really need to see that. So these undergo a lot of ring strain. And so we see that 3 and 4 membered rings are really not that stable. They're going to be more reactive because these rings are ready to pop open because of these terrible angles. So these happen to have quite a bit of energy. And if we're looking between, say, a 6-membered ring, actually I have numbers for a 5-membered ring. So if we look at a 5-membered ring versus a 3-membered ring, we're looking at about 140 kilojoules of energy difference between these two. Again, not a number you'll need to know. But referring back to the conformational torsional strain that we saw with some of those conformers as we're rotating our molecules, we're going to see that this is a much bigger problem. The ring strain is much harder because it's locked in that position. Rings can't just open and close, unfortunately, whereas single bonds, they can rotate around, so things aren't that bad. But when you have a ring, things are forced to be stuck there, and you can't just break that open. We're going to see that things can flip-flop, but they cannot break. You don't break single bonds very easily. So we're going to see that there's a much bigger energy difference between a 3-member ring and a 5-member ring. And while we might be tempted to say, well, let's look at a cyclopentane 108 that's pretty close to 109. Yes? Unfortunately, if we take a look at these things kind of closer up, we do actually have a little bit of carbonking happening here. And as a result, in order to alleviate that, we actually distort our pentagon. You know, we might be saying, oh yes, this pentagon is flat, and we just have our things at 108 there and whatever else elsewhere. But in reality, these things distort a little bit. So they're not planar structures. And we're going to see that as a result, we'll end up drawing our cyclopentanes a little bit differently. We're going to see that we're going to kind of buckle it a little bit. And so we're going to end up having kind of this idea here where we'll have, now we have our H's kind of far away from each other. So we don't really have a flat structure. We have this kind of buckled, they call it an envelope. I don't really see an envelope here, but that cyclopentane bumps around a little bit. And so in reality, we don't actually have 108 degrees. We're going to have a little bit different. And with cyclohexane, I might be so tempted to be like, 120 degrees is not that great. But if we put this in 3D and bonk stuff around, we actually do get 109.5 degrees if we rotate this one. We're going to see, these molecules can actually be tetrahedral if we, instead of having a planar structure, have them kind of bonked a little bit. And then we have, let's see, what's this one going to be? That one will be like that. And then we have another one, H down. So, I'll draw that one like kind of like that. We see that these cycloalkanes don't really stick with planar structures. They will tend to kind of do stuff, they'll kink themselves to try and get closer to 109.5. And in fact, with cyclohexane, we do end up with 109.5. And so we're going to see that cyclohexane 6-membered rings are the most stable of all of these. As we get bigger or smaller than cyclohexane, we will end up getting less and less stable. It's worse to go smaller than 5-membered. That's a huge energy gap. And it's kind of whatever to go a little bit bigger. Bigger ones are still relatively stable. But because of the special kind of stability of cyclohexanes, we're going to be studying those quite a bit more. And so we see that cyclohexanes are going to adopt what's called a chair conformation. Because in some crazy person's mind, this looks like a chair. I mean, I could say, yeah, it's kind of a lawn chair if I kink my head and really imagine, but it's the way it is. So, let's take a look at how to draw a chair. So a hexagon, pretty standard, right? With chairs, I think this is how I learned it. You start with 2 parallel lines. You should end up with 3 sets of parallel lines altogether. You're going to end up God, that's terrible. Okay, let me try that again. So 2 parallel lines. You're going to kind of dink one in, do the same thing on the other side, and do the same thing there. And you'll end up with what apparently is a chair. So I've kind of gone a little too harsh on my angles there, but it's the same idea, right? So that's kind of what you're looking at. If you really want a super nice chair, yeah, you'll want these parallel lines and all that, but I tend to be a little lazier. So like this one, the green ones should be parallel, the blue ones should be parallel, and the purple ones should be parallel with each other, and just slightly skewed off from each other. With the substituents, though, here I'll use my nicer molecule. it's important that we maintain the geometry of these. So whatever is stuck on your cyclohexane, it's important that we keep our tetrahedral geometry. So hopefully we can see from this back one, we kind of have something coming out towards us. This is kind of a wedge. And this one is kind of a dash, so we need to have the other two be those 109.5 that are in the plane with each other. And if we do the same thing, I'm going to get rid of this wedge bit. I hope I can. Okay, good. We now have one going straight down, and as a result, the fourth one is going to be kind of coming up a little bit. We now have a vertex pointing up, so we are going to have that one pointing up. And what's kind of the hard part here is we need our last one is going to kind of be sticking out this way. I think I've drawn them up here actually. So yeah, we kind of have it. Ideally, you want these two to be parallel with each other. Red, ideally. I'm not so great at drawing these, but we want to draw them this way. We go down again. And we go out. We go up. We go down. This one goes down. And we're going to see that one should be parallel there. So we're going to see that that's kind of how you draw these things. Ideally. Oh wait, this one should be parallel with that one. We need to point it the other way. Oh, whatever. So with these, what's important that we look at though is these ones that are pointing up and down. In any chair cyclohexane, everything that's pointing, I'm going to get rid of everything that's not pointing up and down right now. When we're looking at these, when we're assessing the stability of them, we see that these things that are pointing straight up are going to bonk into each other. We call these 1,3 diaxial interactions. And these are always destabilizing. And we're going to see when we're assessing the stability of cyclohexanes, when we have bulky things bonking into each other, those are large 1,3 diaxial interactions. 1,3 meaning there's just a difference of 2 carbons, or rather there's a carbon in between them. If I wanted to number the other one, I could have named that one number 3, or I could have named this one number 1. Doesn't quite matter either way. They're 1,3 that's just in relation to each other. Those things that are axial, as in sticking straight up or straight down, are going to bonk into each other. And so when we have axial things sticking straight up and down, that are big and bulky, those are bad situations. Those are destabilizing. By contrast, so those are what are called axial positions. I always draw that one too short. These guys are axial. They are an axis. The other one is called equatorial. And so we see here again axial substituents will bonk each other, always, forming those 1,3 diaxial interactions. Those are always bad. However, equatorial ones are always, or they don't mess with your molecule. So this one that's pointing down is adjacent to one that's pointing up, which is adjacent to another one pointing up. So there's no kind of equatorial problems here. And this one we have it pointing up again. Oh, I'm out of room there. But suffice it to say, these equatorial things are pointing away from each other. So like one's pointing up, one's pointing down. And so as a result, they don't really bonk each other. With the axial one, everything is all right here. They're all right next to each other. They're bonking. But the equatorial stuff, they're carbons away and they're pointing different directions. So as a result, you know, if we see here, these two are pointing down. By them pointing down, if we compare them to their counterparts that are pointing up, look at how far away they are. So if we're looking at this carbon and that carbon, the axial hydrogens are bonking each other. However, the equatorial ones are pointing far away from each other. And as a result, we're not going to have problems with equatorial substituents. So for bulky things, we do not want them to be axial. Equatorial is the way to go with bulky things. And let's take a look at an example. I'm so bad at drawing that one. Okay. Here, and I'll go crazy with this. All right, let's look at this one. Not so great now. We have our hydrogens that normally would bump into other hydrogens. Now they're bumping in with a frickin' methyl group. Much bigger than a hydrogen. And so we're having much bigger clashes. And as a result, these 1,3 diaxial interactions. Actually, I wonder if I have numbers for these. Those are various conformations. We'll talk about those. I wonder if I have values for these diaxial interactions. I don't have values for them, unfortunately. But suffice it to say, much worse than HHH, having a hydrogen up. In this case, we have a hydrogen in an equatorial position. It would be more favorable for us to have it axially. And in fact, these chair conformations are not static. We will find out that these chair cyclohexanes will very often undergo a chair flip. Every time I draw these, they get more and more lightning bolty. But here's our methyl group. We see that these chairs that adopt these conformations where they're zigzagging, they can just flip right over. They flip, believe it or not. And if you do a chair flip, I'm going to put this in the equilibrium arrow, not a resonance arrow. When you do this, you essentially flip everything. You now say, okay, well, I'm going to say this is carbon 1, 2, 3, 4, 5, 6. You flip them all. Everything that was axial becomes equatorial. Everything that was equatorial becomes axial. And in doing so, we essentially just draw it the opposite way. And so now we see, okay, here's carbon 4. Now 4 is the one that's pointing up. Same numbers as before. that methyl group that was pointing up will still point up as this time an equatorial. In this case, the axial one is pointing down. The equatorial one's pointing up. So on carbon 1, the methyl group is pointing up. We still want our methyl group pointing up on carbon 1. But in this case, pointing up means equatorial. And this time pointing down means axial. We see that perhaps 95% versus 5% are going to favor the equatorial methyl group at a given temperature. So chair flipping happens all the time. When you flip your chair, you make everything axial into equatorial and everything equatorial into axial. Everything that's pointing up still points up. Everything that's pointing down still points down. So we're just rotating things, kind of. But suffice to say, all axial become equatorial. All equatorial become axial. So since we had an axial methyl, it will become an equatorial methyl now. So one that's not pointing straight up and down, it's now pointing off to the side. Off to the side is always more stable, right? So that's what we're looking at there. So when we're flipping things, we essentially are drawing kind of a mirror image of our lightning bolt, our chair, apparently. And then we're just going to make sure that everything that was pointing up still points up, everything that's pointing down still points down. And so pointing up doesn't necessarily mean axial. In this case, pointing up is axial. In this case, pointing up is equatorial. The axial one's pointing straight down. The equatorial one's always at an angle. In this case, the equatorial one's pointing down here at an angle. In the right case, the equatorial one is pointing up at an angle. Our axial things are straight up and down. So that's kind of the key here. So when we're comparing stability of chair cyclohexanes, this is a lot of your homework, the latest homework. You have quite a few, let me see, where is it? Quite a few chair conformations that you're going to be looking at, and we're going to be looking at how to relate these together. So if we want to look at chair cyclohexanes, we'll be able to compare all sorts of different combinations to each other. We can see sometimes things that are cis to each other, we may be able to get a good chair out of. Sometimes things that are trans to each other, we want to get a good structure out of. I think, though, I don't want to start that part today. Suffice it to say, though, if you really want to start your homework, this would be, for example, looking at problems. Those are, oh, we have plenty of Newman ones there. Number 12, for example. We can start on those. We can draw them as one chair and then flip it and see what happens when these things are related. So number 12 is all about comparing chair cyclohexanes. So is number 5, actually. Although those have names, so you'll have to draw a structure first and then go with a name. So we're working on it, bit by bit. We're getting there. We're going to add more and more kind of things to our tool case here. One thing I do want to point out, these two that I've drawn here, these two chairs represent this molecule. Notice that in both cases our methyl is pointing up. It's a wedge. Remember, wedges are pointing up, kind of. So notice in both chairs our methyl group is pointing up. So if you see things that are on dashes, things would be pointing down. In this case, it doesn't really matter, as we'll find out next chapter, but say if these two things are like this, these would be trans to each other, right? They're on opposite sides. One's on a wedge, one's on a dash. This is a methyl pointing down. These are trans to each other. Remember, trans means the opposite, so that one is pointing up, one is pointing down. Those are trans. If they're both pointing up, they're cis. Or both pointing down, they're cis. But in this case, these ones are trans to each other. So we'll see how that's going to look when we look at the chairs of this particular molecule next time. So, because we're a little bit out of time today. And then we'll talk about double Newman conformations when we start putting cyclohexanes into Newman conformation or Newman projections. We start looking at two things at a time. We'll look at those. So we'll get to that on Wednesday. Hopefully the tears are flowing. There's so much to talk about these alkanes that deals with their stability. And as we're going to see, stability is going to predict reactivity. So all these sorts of things are going to be important for determining how things are going to react later on. So there is a method to the madness eventually. There is somewhere we're going to go with all this stuff. So, but for right now, lots of practice. That's what this is going to take. That's why your homeworks are so long, is because I've got to give you tons of practice getting used to all this stuff. So it's a lot of work. This will probably be one of the hardest classes you will take. And I'm sorry. But the reasons that there are horror stories about OChem are for these reasons. So you will become masters at drawing hexagons. You'll become so good at drawing chairs. I'm still not very good at drawing chairs, but you will become good at them. So don't worry. All right, so have fun. Start taking a look at your homework. See if you can maybe even start some of these cyclohexanes. Just make sure that if things are pointing up in your kind of wedge dash structure, that in your chair they're still pointing up and pointing down otherwise. So, all right. Fun. So, Wednesday we'll continue this stuff. And Friday we'll have a review. Either from any of the stuff. We're on chapter 4 now, so any of the stuff from the beginning up till now is fine. You know, you guys are probably wishing you had more resonance problems instead of dealing with these silly chairs, but that's what we're going to do. And then we'll talk about boat cyclohexane too. You thought you were done? No. Alrighty, but that's enough terrorizing you for today. So we'll continue on Wednesday. So I'm going to put our poll in Discord now so we can see when you guys would like to review. So, alright. Enjoy the rest of your day as much as that's possible, and I'll see you Wednesday.